Hello. All right. Welcome, everyone. We are going to get started in the interest of time. So my name is Alex Hyder. I'm Director of Game Developer Programs at NVIDIA. It's my pleasure to welcome you this afternoon to what's a big day for us. It's our unveil of RTX, our new ray tracing technology, and we're very excited to be able to show it to everyone today. So this is our second talk. And we have three speakers with us today: Morgan McGuire, Patrick Klarberg, and Nir Benti from our NVIDIA Research group. The talk is divided in essentially two sections. The first is talking about the roadmap for ray tracing in gaming over the coming years, and then the second one will be a little bit more of a deep dive into what we've got today. One last thing, we do have a giveaway for a GTX 1080. We'll do that right at the end of the talk, so stick around. Thanks very much.
All right, thank you, Alex. So real-time ray tracing is coming to games. On NVIDIA hardware today, it is powered by our RTX technology, and that's exposed through the cross-vendor Microsoft DXR API. This is something you'll be able to use right away. And ray tracing is one technical feature, but it's going to have an outsized impact on the way that you produce games. This is one of the cases that I think is like the advent of programmable shading or online multiplayer, where there was one technical ability came online, and it completely changed everything about the workflow of how you created games. And so I think that's the real payoff. That's what I want you to keep in mind about today's talk. It's not about the details of ray tracing per se. It's about what that's going to change about the cost and workflow of production. And in this talk, we're going to put today's game development in the context of today's technology, and then fast forward that through a couple of years to give you a roadmap of what we think is coming, and so that you can be prepared and that you can embrace the power of ray tracing, both for visuals and for workflow. And we're basing this on a lot of internal prototyping that we've been doing over several years, knowing that this day was coming. And we're going to be revealing for the first time today some of the images and some of the ideas behind what we call hybrid rendering, ray tracing meets rasterization. And so we're going to use that, and then a lot of deep dive collaboration and interviews we've done with film production in order to look at how the advent of ray tracing between 10 and 20 years ago completely changed their pipelines, and look at what's going to work for games that's going to be similar to how ray tracing affected film, and what are cases that are actually unique to real time, where we have different constraints because of interaction. So usually, I would give acknowledgments at the end of a talk. For this talk, because there was such a big impact from so many people, I want to take a moment to thank both our external film production experts, and you'll see sort of a lot of their wisdom implicit in the ideas that we're presenting today. And then a lot of our internal NVIDIA colleagues and also some external engineers who've worked with us on the work that you're going to see today. So this is really a cast of thousands kind of presentation, and Patrick and I are just showing you the ideas. So here's a timeline for games in about 3 slides. And again, keep in mind, it's not about the technology. It's about how the technology affects the artist's workflow. So if you made games before programmable shading, and a few of us in this room probably have, from looking around, you're a legend, right? There was almost nothing you had to control the visual look. It was all about really low-level tricks. And from our perspective, that's kind of antiquity, right? Like we live in awe of these games from the pre-programmable shading era, but they don't directly speak to the kind of workflows and the kind of visuals we get today. So it's, things like Half-Life 1, right? Great game, but not remotely comparable to what we're doing today. And then the world that you live in if you're making games today probably involves technology like these. And this is the era that I claim ended on Monday. You have rasterization, and that's it. And you have programmable shading. And programmable shading over about 2 decades has given us amazing power. Right? We've seen the incredible speed up of GPUs. We've seen the incredible fidelity of games. And it's taken a long time for people to learn how to master this, but we can make amazing visuals now. But it also means you live in a world where you have shadow map cascades and bias and separate shadow maps for the hero shadows, or you have screen space effects that look fantastic in the best case and that you spend months tuning in the worst case so that they don't completely fail. So your reflections and your AO are going crazy all over the place. You have no good solution for transparency, even though we've created a lot of stopgaps that in special cases will give really high quality results. It's something that has to be hand-tuned for every scene and every material. And then when you really want good quality lighting, what do? You actually use ray tracing and you bake your light maps and probes offline anyway. So you're already using ray tracing, it's just it's an offline production process. And the problem with that is it gives great quality, but an artist moves the light and then they wait 1 minute or 10 minutes or 20 minutes to see the lighting change in the level. And so production is blocked today on artist time, right? That's what we're limited by, not engineer time. Because artists are spending so much time working around all the limitations of the real-time techniques. They're just too complicated to go much farther under rasterization techniques alone. And then the artists themselves are blocked on the baking process of ray tracing. So I think you're a hero if you're making games like this, because the amazing thing is that the games that are coming out today look almost as good as offline rendered films in some of the best shots, right? So we have really unique looks across a variety of hardware, a variety of platforms. People are getting the performance up there, they're getting the visuals, they're getting the visual fidelity, they're getting the complexity and the shading. But again, it's not because it's inherent in the engine, it's because of the heroics of the art team and the engineering team, and they've kind of hit the limit. We just can't afford to produce games with art teams that are twice as big or twice as many techniques shoved together. And so what happened on Monday with the advent of real-time ray tracing being directly integrated into a cross-vendor API is you can now immediately, and I think we're going to see games in the coming months, that ship in sort of a Ray Raster Coexistence, where you take all of the great things that we've gotten out of our raster pipelines, and then you start using ray tracing to make it so that baking isn't an offline process. It's a slow, interactive process for the artist. But they don't go get a coffee when they move the sun. They just wait 4 seconds and it converges. And where the probes maybe can be dynamic at runtime. So we start using the structures we already have, but the line between runtime and production starts to become a lot more fluid and a lot more dynamic. And you're going to see reflections and hard shadows. And there's all kinds of great stuff at GDC now about exactly how to do these and how to start rolling that out on technology that's available right now. And what's interesting about coexistence is, to me, that's the point where film was exactly 20 years ago. This was peak rasterization for film. And Pixar's A Bug's Life perfectly captures this. So absolutely beautiful film, has great global illumination, which is all done by artists hand placing bounce lights. It has ambient occlusion passes, it has shadow maps, it has screen space effects. It has all of the technology that would be extremely familiar to anyone using a real-time game engine today. And it had all of the production problems for that. There was just no headroom. They were spending all of their time manually tweaking shots to get them good. And they actually have an advantage over us, right? Which is, it's not interactive. So A Bug's Life, you render the shot, and if the techniques all kind of blew up because of the combinatorial explosion, then you just tweak it and re-render the shot. In the game, it's got to work reliably, even if somebody moves the camera or the light at runtime. And then the coexistence is that to get the water in the glass, there's a couple shots of the refraction in this film. That's where they added ray tracing on top. Right? So it was peak rasterization. This was sort of the height of micro-polygon rasterization on RenderMan. And it was beautiful, but it was the ceiling. And I think that's the coexistence. And so the coexistence is this year, but we need to get out of that mode as fast as possible into the new era, which is going to be true hybrids. And so what's coming, and this is what the rest of this talk is going to be about, is how do you take all the good stuff from rasterization and put it together with the good stuff from ray tracing and end up with an engine that's simpler and faster and easier to understand, and where your artists can work 4 to 5 times faster, which is exactly the kind of speed-ups that film saw. So it's production speed-ups that we're really concerned about. It's okay to lose half a millisecond maybe if I can put twice as many, get twice as much throughput out of my art team in the process. And we're going to look at specific ones of these. Let me give you the high-level strategy of what it means to embrace hybrid rendering. And we want to get from A Bug's Life to something like Coco. And specifically, A Bug's Life had all of that kind of game-like technology in it with the shadow maps and the separate passes. Coco is just pure path tracing. They cast 64 samples for every pixel. Sometimes it scales up to 256, and that's it. There are no shadow maps. There's no separate lighting passes. It's just, this is all done in camera. And that gives you incredible workflow, but it also gives you the incredible visuals. So what you need to do is start redesigning now. You need to embrace rays now so that just like programmable shading had this incredible performance curve, that's going to happen again for rays, and you want to be right in on the ground floor to ride that. And you need to think of rays as not just a VFX tweak for today's games, but a fundamental primitive throughout your pipeline. So the easy place to get started is if you're already using ray tracing for physics, if you're already using ray tracing for baking, GPU accelerate that now. It's built right into DirectX. There's no reason not to put that right into your pipeline. And then start looking at those pain points. What are the places where your artists are spending a lot of time tuning to work around the effects? So something like maybe screen space ray tracing for reflections. There's a really obvious transition from there to ray tracing. Maybe ambient occlusion, where you're using screen space samples for visibility. Maybe that goes straight to ray tracing, and it doesn't affect the rest of the pipeline right away. And then start thinking about, as you go through all aspects of production, as you go through all aspects of revising your engine or your title, and think about where are places where we assumed it was raster? Where are places where we assume that if I'm scheduling a warp on a GPU, that the adjacent thread lanes are adjacent pixels? Because maybe that's not going to be true in the future. Maybe you need different ways to think about what it means to have shading coherence or material coherence. How would you do filtering if you didn't have screen space derivatives inside of DirectX, if instead you have to do it based on a ray cone? And there are all these places where there are opportunities to sort of revisit what we've baked in and say it doesn't have to be that way. That was an artifact of a rasterization pipeline. In the long term is we think we're going to end up basically where film is, with a different style of engine, but the same algorithm, which is full-blown path tracing. And that's going to be made possible because of denoising technology. That's what took film down from thousands of samples per pixel to maybe hundreds to sometimes only tens of samples per pixel. That same technology is what enables real-time path tracing. So that's coming in a few years. We're going to show you some of the first examples right here today and start thinking about what that means for your engine. And the general hybrid rendering strategy is straightforward. It's just think rays first. And the rays are really fast, but they're not free. So first you design your algorithm based around rays. You say, hey, a shadow is a place where I cast a ray and it can't hit the light. And then you step back and say, well, but I still have a lot of optimization I can bring in from raster kinds of techniques, from existing real-time rendering techniques. So maybe a shadow is a place where I cast the ray and it hits an occluder and so it's dark. But I don't have to cast rays everywhere. I can still use a shadow map to know when I'm fully in shadow or fully in light. And maybe I only need rays right at the transition region. And so I can take a few rays and get a lot more mileage out of them than just by brute force. And then the big take home is there are a lot of high-level algorithms, especially in the last few years, that have been developed. And I just heard today, thank you, Natty, that Real-Time Rendering 4 will be coming out. So it's about 1,500 pages. And a lot of that stuff that's not going away because it's high-level ideas. So things like processing in tiles, that's really a GPU operating system scheduling kind of idea. It's not inherently a rasterization idea. You can still use it. TAA, geometry streaming, occlusion culling, these are all compatible with ray tracing. So we can keep these kind of speed-ups, but then we can use rays to get the robustness and quality. And now I want to dive right into some of these case studies. And for the first time, we're going to show you some very early production work. So this is not shipping. This is not ready to be published. But this is some of the stuff we've been doing behind the scenes, embracing this idea of hybrid rendering. So Patrick, can you show us some of that?
All right, thanks, Morgan. That was a very visionary and great introduction. So I'm going to now talk about some of these kind of early, in some cases early prototypes, but directions that we think are promising directions for solving problems that have traditionally been very hard with raster-based real-time graphics. And I want to emphasize again that none of this is finished products. It's merely directions we're looking at that we think are going to be important for future game engines. So one class of algorithms is, as Morgan said, these hybrid Ray Raster algorithms where you mostly use extra rays to augment or improve the quality of existing raster-based solutions. There's a number of areas, we can list many of those, but one that I think is quite illustrating this in a good way is work we've done at NVIDIA about, it's also collaboration with Unity and ILM X Labs, work about how to shade and get correct shadows from area lights on glossy surfaces. And this is a pretty hard problem. We've seen that over the last few years, there's been methods developed for evaluating analytically the lighting through linearly transformed cosines, for example, but then you ignore the shadowing term. If you go to the other end of the spectrum, you can potentially do stochastic sampling of your shading, shoot random rays and evaluate your shading with the glossy term, but that leads to very noisy results. So none of those are a perfect solution. What people tend to do maybe is to take shadow samples, either from a shadow map or now maybe trace shadow rays, to approximate and average those shadow samples to approximate the visibility. But the fundamental problem is that the shading and the shadowing here are correlated. You can't evaluate shadow in one direction and do shading in a different direction for a glossy surface. It just doesn't lead to the right result. So if you do the shadow term, modulate the glossy term with that, you get this effect on the third image that the glossy reflection kind of fades out, which is clearly incorrect. So hybrid algorithms solve this. I think it's best illustrated through pictures. The algorithm outputs first the unshadowed area lighting solution using linear transformed cosines. As a second output, it produces a noisy but correctly sampled shadowing. So in this case, there's a few, maybe only one shadow sample per pixel, but it's evaluating the full BRDF. Then, by filtering this noisy picture, and dividing the two, dividing the analytical incorrect solution by this filtered and correctly estimating solution, you get the shadowing term that is actually a very good correction term for your shadows, unlike the just average visibility we saw earlier. So if you take this shadowing term, start with your unshadowed image and apply that. Then you have a nice stable area light shadows that works on both diffuse and glossy surfaces. So I think this is an illustrative example, but I think it's a good example showing that through a small number of rays per pixel, you can augment an existing algorithm and produce much nicer results. Another, maybe a little bit easier to explain, use case is to simply replace or augment your existing screen space ambient occlusion paths with a very small number of stochastic samples sent through ray tracing. And these rays are cheap to trace because they're both shorter and you don't do any expensive shading at the hit points. So here's an example with two samples per pixel, and then fairly standard denoising filter, some kind of bilateral filter. And then comparing that to ground truth, it's not exactly the same, but it's a lot closer than the screen space ambient occlusion algorithms. And you can also imagine doing a hybrid where you take samples from screen space and then augment those samples with rays to produce a nicer result that's very, very close to ground truth. So now let's switch gears a little bit and talk about what makes us really excited as researchers. And that is, of course, dynamic global illumination, solving the real lighting problem. So I'll talk about a couple of different solutions, but at a high level, they more or less boil down to the same fundamental steps. But before we go to that, I'll show just a little illustrative example here with a video. In this case, there's a single light source outside the room, so the majority of the scene is lit indirectly through light bounced off the floor and bounced off the furniture. And this was rendered using path tracing using 1,000 samples per pixel. You can see that it's still noisy, so that illustrates the complexity of doing the full lighting simulation. The first observation we can see in this video is that the lighting changes at very different rates. At some parts, where the geometry is moving, or the light is starkly moving, it's changing very quickly. But then other parts of the scene, the lighting is almost static. So for example, behind the sofas, some corners of the room, there's almost no change. So of course, we're going to exploit that and avoid recomputing things at places where it's not needed. So how would you do that? How would you go from 1,000 samples per pixel down to realistic budget of maybe one stochastic path per pixel, one or a few? So I'll go through a number of different steps in an algorithm to sketch out how you can do that. The first is, let's use temporal accumulation. That's a favorite trick. It solves all problems. A neat thing about ray tracing is that while you shoot your rays, you can almost for free compute extra ray heuristics. For example, the distance at the hit point from where you shot the ray from, that directly gives you the distance to how far away an occluder is. Similarly, you can evaluate motion vectors in object space at any hit, and you can evaluate such heuristics at any point in the light transport simulation. And the idea is then to boil down, ray heuristics collected through ray tracing into something that can control the rate of temporal accumulation. So that you accumulate and let it decay slower in areas where it changes slower, and then refine the solution faster in areas where the light changes faster. So in this video, we've just done this small test for this. So I'll play the video. It starts off blue. It's color-coded. Blue means that there's no reuse from previous samples. And then you can see that as time goes on, some areas converge quite quickly into regions where it's with red, which means that there's a lot of temporal reuse, while other areas are not changing. Other areas need to be updated faster, so they're blue or green in this case. So this gives us, a little bit. It gets us some a little bit towards the solution, but it of course doesn't really solve the problem. And I think you're all wondering, what to do about ghosting and all these other problems with temporal accumulation, because you can't really accumulate over hundreds or thousands of frames using temporal accumulation in screen space. And those problems are mainly an effect of that working in screen space. You have to reproject using motion vectors. You have problems at the screen boundaries. You have problems with disocclusions when an object moves, the pixels that become unoccluded that weren't previously seen. So let's not do that at all. Let's not accumulate in screen space. Let's accumulate in a different space that doesn't have these bad problems. And one of those choices is accumulating in Lightmap space. So an outline of an algorithm would be use Lightmap space as a cache for illumination. Don't see it as a static lighting solution. Use it as a cache. And then use ray heuristics collected during ray tracing to guide the fall-off and refinement of that cache. So you only refine it where it's actually needed. And then an important other component is that if you're caching things in a data structure like a light map, you can actually use that cached illumination as input to the lighting solutions for the next frame. So that means that you can refine the lighting by letting the lit texels from one frame be input to the next frame. And over time, refine the lighting so that light bounces one bounce per frame. And that gives you a huge improvement in noise levels. Of course, the drawback is that there's going to be a slight temporal lag in the indirect illumination, especially in higher bounces. So if you have a case where light shines into a room and it bounces many times to hit the dark corner somewhere, the light to that corner is going to be delayed compared to when the light actually came in. But fortunately, that's quite a forgiving. It's one of the nicer kinds of artifacts. It's much better than a ghosting or an immediate visible artifact. Then, of course, you can't get away without the denoising filter. Denoising is really key in all kinds of ray tracing algorithms, realistically speaking. In this case, you can apply a filter in Lightmap space. You can do it in screen space or a combination of the two. And I don't think we have the final answer on exactly how and where to filter, but it's a combination of those spaces. I'll show some examples. So on the right here, you see the conceptual pipeline implementing this kind of algorithm. It always starts with the G-buffer pass that lays down your inputs to your ray generation shader. Compute pass defines where to update your lighting, then shoot rays and refine the lighting in those areas, apply a denoising filter, and consume the data, and do the same for the next frame. So thinking about this for a while, there's nothing really unique in using Lightmap space. You can imagine a very similar algorithm operating in another data structure. Lightmaps is just a data structure keeping the illumination. So potential choices could be light probes distributed in volume. You can also think of potentially using voxel structure or a world space hash, similar to what stochastic progressive photo mapping is doing. The important thing is you need some place to cache your illumination so that you can refine it over time and denoise it. And as long as you have a data structure to cache it in, you can apply similar kind of algorithm. So I'll show some examples of different prototypes where we tried this. These are early results from a rendering pipeline based on these concepts in Lightmap space, which was developed by our content tech team at NVIDIA. So here is the noisy the raw one sample per pixel indirect illumination. And as you can see, there's not a whole lot of data to work with. There's a few random pixels here and there that have a gray value instead of a black. But that's basically the input. And on the bottom right, you see the reference image, what it should look like when the full indirect illumination solution is computed. So I'll play the video now. We can see it starts black because there's no reuse, and then over the first few frames, it's going to converge to the actual solution. And then there's some dynamic objects in the video. We can see that lighting is indeed updated. And if you look hard, you can see a slight lag in the updates, but it's fairly forgiving, I think. So look at it. So in this scene, the light is only coming in through the windows you see in the back that are black in this case. So obviously the quality is not 100% perfect. There's some blotches and so on, but you have to compare it against the image we saw before with the one sample per pixel, which is really the actual input to this. And this is running in real time on a single GPU. All right. So another solution, that was showing Lightmap space. Here's another example using a world space hash instead. So what a stochastic progressive photo map would be doing. Conceptually, it's very similar. It's caching illumination in that other data structure, refining it over time using the previous solution as input to the next frame, and then denoising it. So here's the input again, one sample per pixel, and then denoised output. So I think this looks, it looks promising. These conceptual steps, I think they're going to be part of a future solution for, a product-ready dynamic global illumination solution. Of course, a number of tweaks left to do, and we also need to evaluate, where is the actual performance, how many rays can you get away with to do this in the fully complex scene that games have. As a sidetrack, we're still investigating. Can we actually do without the data structure that globally tracks the illumination? So I'll show some examples of how far we've got in traditional screen space filters. So here's input again, path trace. You get the idea. One sample per pixel, and then an advanced screen space denoising filter. This filter is based on temporal computation, starting with that, then using a cross-bilateral filter in screen space that uses noise-free guide images that are output by the G-buffer pass to guide the bilateral filter. And then it has a noise estimation step that really helps you pick parameters for the bilateral filter. And then this whole process is iterated 2 times, 2 different spatial scales. And that allows you to remove the noise both at the fine scale and broader to avoid blotches in the image. So now I'm going towards the last section of our case studies. There's, of course, now a lot of focus on using ray tracing for intersecting triangles. But it's not the only thing we can do with ray tracing. And the DXR API actually supports custom intersection shaders. So you can put bounding boxes in a data structure, and then in the shader yourself compute an intersection. So why would you do that instead of just doing it in compute in the first place? One is to get NVIDIA RTX acceleration of it. If you do it compute, then you're bound by the regular. There's not so much we can do to optimize it. The other thing is that with DXR, you get actual shader evaluations at the hit points, and you get individual resources bound to those shaders. So it allows a lot of flexibility. One use case is intersecting hair strands for hair rendering in one of these custom intersection shaders. And you can generalize this to other small and thin objects, wire, fences, arrows, things that when you move away that are distant, where triangle rasterization is just not the good solution anymore, where you end up with just a flickering mess due to all the small triangles. So in some cases, ray tracing can both be faster and give you better quality for these difficult objects. So here's an example of real-time hair rendering. So we have internal work that has managed to solve these intersection tests very, very efficiently. So that you can intersect not only 100 or 1,000 hairs per frame, but actually do it on a full hair model. So this is from a very hairy person with over 1 million hairs. And it's rendered in real time by intersecting the actual geometry through custom intersection shaders. On a similar note, you can do the same type of algorithm for rendering tessellated geometry. So fundamental problem with tessellation and ray tracing is that normally you would have to tessellate your mesh, then build an acceleration structure of the tessellation, and then trace against that, which can be fairly expensive. Instead of using a custom intersection shader and doing the analytical, doing the subdivision inside your shader, it's often actually a preferred approach to it. So I'll show a video here which is running. This was done a few years ago, so it's running in optics on an older GPU, but even then it was real time. So it's ray tracing subdivision surface on the GPU. So the next step in this is, of course, port this to DXR and use it on real big assets. But it's showing as a proof of concept that it's a feasible approach. The benefits is that you get perfect normals. There's no artifacts from tessellation anymore. You don't work with a triangle mesh in this case. So that concludes the case study section. I hope this has inspired you to think about how can we use ray tracing in your future productions and game engines. We'll switch back to Morgan for a while.
All right, thanks, Patrick. So we think a lot of those are really exciting examples, and the cool thing is that they're all running real time today on Titan V in our lab. And so we think that's exactly the kind of stuff that you can start experimenting with now, and that we're going to start seeing techniques based on this hybrid rendering idea coming out into production in the next couple of years. And again, think about how they affect your workflow. Right? Don't focus on, will this effect give us this visual quality? First, look at, you already have great visual quality in your games today, whether it's in Unreal or Unity and prefabs and stuff you've done in-house. Games look great. Start looking at what are cases where it cost us too much to make it look great, and how can ray tracing accelerate that? So design first, around rays, right? Cast real rays, maybe only 1 ray per pixel, maybe 2 rays per pixel. Then step back and say, okay, we now have the look we want performance. Well, let's take some of the pieces of the existing screen space techniques that are efficient and bring those in, but only in cases where it's not going to compromise the workflow the way that it is today, and keep all of that good high-level stuff going. And I think that the most important thing, the message of sort of the research talk we want you to have today is you're going to see a lot of really cool demos at the show of ray tracing is shiny reflections, because that's the easiest thing. You can drop that into your engine in a day or two. And then you're going to see shadows and other things. And it's true, like ray tracing is shiny balls. You can have that today, right? There will be spheres and they'll look great. The point there is not just to, not to have reflections be the lens flares of 2018, right? The point is to go a little bit further and get to where, when you really integrated this technology into your workflow, you're going to get cinematic quality light. You're going to get all of that robustness, all of these subtle effects from a really streamlined pipeline. And it's going to give you the opportunity to customize your pipeline again. We're at the point where there are 20 people in the world who can optimize a cross-platform, cross-vendor, PC, console, high-quality engine. And it's just because it's too complicated. You touch one thing and something else pops out. Ray tracing has the potential to bring us back to the point where we can all innovate and experiment, and each studio can use the same set of engine tools but have a really unique look and optimize in unique ways. So you also get that. But the big take-home is something I can't show you a picture of directly, which is that you're going to get back to the point where your VFX programmers and your artists have headroom again, right? Where our workflow allows us to go back to being where we were even just a few years ago, being really creative and starting to explore new looks and new mechanics inspired by those looks. So I'm going to leave you with a happy artist, because that's the payoff of ray tracing. Okay. And in closing, before I introduce Nir, because Nir is going to take us through Falcor, some of our internal prototyping engine, which is going to be available to you on GitHub, is I want to recommend, I just got permission last night to say this. So the ACM transactions, the next volume that's coming out, which will probably be before the summer, is a deep dive from all of the major film production rendering teams about how they built their renderers. This is a message in the bottle from the future to us, right? It's them telling us how they did everything that we're now looking at for the next decade. So I highly recommend that, as well as 2 earlier papers that really talk about exactly how film and predictive production rendering work. And if you want to be a piece of writing the other articles people will be reading, I'm pleased to announce a call for participation in Ray Tracing Gems. So this is an NVIDIA new book series we're launching with 2 of the editors, Eric Haynes and Thomas Akinine-Moller, who are at NVIDIA, who are 2 of the editors also on the real-time rendering series of books that you all know and love. And so we welcome submissions to that. So thank you very much, and I'm now going to hand off to Nir, who can tell you about Falcor.
Thank you, Morgan. So I want to talk a little bit about how we do research at NVIDIA, and what we have is Falcor is our real-time rendering R&D infrastructure. We started it 3 years ago. It was focused on rasterization. We just wanted a common tool for all the researchers to use. It evolved over the year. It literally changed the way that NVIDIA invents new rendering ideas. It's increased our idea throughput, improved our collaboration, and basically allows us to work on harder problems, solve harder problems that the industry is facing. So why do we need it? I'm sure many people here have their own private framework and are aware of stuff like the XUT that we have in the past that people were using. And when I joined NVIDIA, every researcher did use his own or hers private personal framework. In fact, how many people here are using their own framework to prototype stuff? Yeah, oh my God. Okay, so for the most part, those frameworks are pretty simple, right? They provide basic GUI, probably a model loading, and texture loading support. And as a consequence, the image quality is pretty basic. Use basic assets like Sponza, everybody uses Sponza. Basic shading, mostly direct illumination. Maybe we implemented basic shadow maps. And for us, that proved to be problematic. So NVIDIA Research, our research ideas end up in engines and end up in products. And what we found out is that you do research on Sponza and something that look like that, but games don't render that image quality. Render games looks like this, and this is the Infiltrator demo. This is from 2014, I think. So games look amazing. And when we used to work, you know, you have this brand new fancy anti-aliasing technique, and you get it to work on Sponza, then you try and integrate it into an engine, but the engine has particle system, and it has indirect illumination, and the specular highlights are high frequency, and your fancy idea breaks, and then you have to start tweaking it inside the engine. And we found out that we just wasted a lot of time, like, you know, going back and forth. I was actually, you know, after I joined NVIDIA, we started talking with game devs. I was surprised that it's not an NVIDIA research only problem. I've had some discussion with game developers, and they're facing the same issue. Thing is, game engines constantly push the boundaries of visual quality, yet our private rendering frameworks don't really evolve. They stay in the same place, using the same lighting model that we've been using 20 years ago. There's a huge gap there in terms of visual quality, and this is one of the things that Falcor tries to fill. So what were the requirements? When we started thinking about Falcor, the requirements that we had in mind was we want to reach 70% of AAA engine image quality. And we feel like 70% is a good number. Reaching 100% is going to be very hard because game engines are complicated. And they use a lot of techniques to get, you know, the visual quality, and I don't think it's feasible to do that in a framework that's supposed to be simple to use. And we do want to keep the simplicity of the framework. We don't want to build our own engine and work in there. We want something that is simple and intuitive, and I'm going to show a code example in a second. And we also always want to support the latest technologies and APIs. Someone want to ask me, why don't you work in UE4? It's open source, but we don't want to wait for other people to go and add DirectX ray tracing and stuff like that. We want to be able to always be on the cutting edge of technology. And how does that translate to Falcor? So we actually have 70% of AAA engine image quality. We implemented a modern physically based shading system. We have a large modular rendering techniques library. We have an API abstraction layer with very clear and simple interfaces. It's only 50,000 lines of code if you compare it to game engine that has like millions of lines of code. And in terms of support, like I said, we're always on the cutting edge. We're going to release DirectX ray tracing support inside Falcor in early April. And DXML is coming in early May. And we're always integrating the latest technologies into Falcor. So what does that allow us to do? Basically, we can start working on a basic asset. You can see no shadows, no nothing, just like very basic lighting, like we used to do in the past. But once we have some confidence in our technique, we can just load a more complicated asset, something like shader balls and add shadow maps techniques that are part of Falcor. And once we feel like we're ready for prime time, maybe we take it into the Sun Temple, and this thing uses light probes and like diffuse GI. And so we can take our basic technique, you know, and scale it up until we feel ready to actually take it and integrate it into an engine. We don't have to work with Sponza all the time. So that's kind of like how Falcor was until a few months ago, and then Microsoft started talking to us about DirectX ray tracing, and we felt that this is the future, and we really need it inside Falcor. So as soon as we got the binaries, I just sat and like added DirectX ray tracing abstraction into Falcor, and again, it allows us to start, you know, with basic assets, write basic path tracers, and then start scaling our techniques up to more complicated stuff like the Amazon Bistro. And we also have scaling support. I wish I had a video for that, but this Mac is actually running around. And, you know, we can do ray trace reflections and filtering. I want to talk a little bit about how Falcor can help you do DirectX DXR prototyping and research. So we have an abstraction layer, and why do we need an abstraction layer? And I've been talking to people, and some people, have been asking me, we don't need abstraction layers. We like to work with raw API. I want to start with a story. So a couple of months ago, we started, working with some of our game developer partners, and we gave them Falcor with DXR support. We gave them that because we wanted to give them like a reference implementation of how to use it with some tutorials. We didn't expect them to actually use it. But what happened is like 24 hours later, they sent us a video. They took our basic ray tracer. They added ray trace volumetric fog rendering. It took them like 2-3 weeks to integrate it into their own framework, into their own engine at the end. But in like the first few weeks, they sent out a bunch of videos because Falcor allows them to actually go and play with DXR without having to wait for that integration into their engine. I know a lot of you don't have the resources to actually go. Like if you're a big game developer, then yes. But if you're just like to go and mess around with the DXR or something like that, you don't want to go and implement the entire API. So that's why we have an abstraction layer. A new API takes time to learn. We're going to save you that time by giving you, and I'm going to show that on the next slide, a code example. We want you also to focus on your algorithm, not the API. So DirectX ray tracing, I want to say that it's complicated to use, but there are like, it's a big addition to DX, and it's kind of like abstract the API once. Let's focus on the algorithms and the problems we want to solve, and not how to use the API. It allows for a fast turnaround time. We can test many more ideas in the same time on different assets. And lastly, the abstraction layers contains many non-obvious optimizations. For those of you who were in Ignacio's talk an hour ago, he mentioned some things that we need to do with the acceleration structures and how to update the shader tables. Falcor is going to take all care of that for you. And again, we have some examples. Once when we worked on DXR and the research team, like we had 5 different applications. At some point, we realized something was running slow. Instead of going and optimizing 5 different applications, we just optimized Falcor once, and people updated Falcor, the library, and they got an optimization, and it sped up their sample. So, like I promised, coding time. I want to show you how to write a basic ray tracer that shoots a primary ray, shadow ray, and does some simple glossy reflections inside Falcor. Anyone wants to guess how many lines of code it's going to take us? Ballpark, hundreds, thousands? Okay. The only thing you need to know about DXR, I want to show the API, but the only thing you need to know about the DXR is the ray tracing pipeline. It's going to start with the ray generation shader. Then we're going to do the traversal, intersection tests, and at the end, if there was a hit, a closest hit shader is going to get called, and if not, we're going to get a miss shader. Literally, that's the only thing you need to know about how DXR works. You don't need to know anything else about it. So, this is our own load code. The first part basically creates our miss programs and our hit programs. You can see there are 2 types of shaders. We create a primary miss and a shadow miss, and the same for the closest hit shaders, and a single ray generation shader. We use those programs to create something called ray trace program. And from that, RT program bars. Basically, this is our data structures where we're going to bind all our materials and all our shader constants. This thing, for those of you who know DXR, this 7 lines of code is the part that's going to basically create a very large part of the ray tracing pipeline state object. The next part is loading a scene. Behind that single load from file call, we're going to create the acceleration structure. There's like, I think, 200 or 300 lines of code there. And the scene renderer, which is just a helper class that's going to help us bind materials into the shader binding table and dispatch the ray tracing call. Finally, we need to create our ray tracing pipeline states and set the program into it. The mock trace recursion depths basically say we're going to have 2 trace ray calls inside our shaders, one from the ray generation program and one from our closest hit. The last line just creates our output texture. This is everything we need to do in OwnLoan. This is going to create our shader binding tables, our resources. Our acceleration structures is going to compile all the shaders. This is our on-frame render. First thing we want to do, we want to update our scene in case we have dynamic object there. It's going to move the camera, animate any skinned objects we have in the scene. This part just sets, like I said, our ray trace barbs is the way how we bind variables into the shaders. So basically, we bind some variables into the constant buffer. You can see the code is very clear. You know what it means because you can tell that we gonna bind an inverse view matrix into the constant buffer. Set the texture as the output and render scene, and this is again going to go and it's going to bind all the textures and all the materials and update the shader binding table in an optimized way, and then call ray trace. And finally, we're going to bleed it. That's everything we need to do in the C++ code. The last thing I want to show you is the primary ray CHS. For those of you who know ray tracing, I'm skipping the ray generation shader because it's pretty simple. I want to focus here on two things because the first part is raw HLSL code, so I'm going to skip it. I want to get to that part, which is get vertex attributes and prepare shading data. This is the part that is going to invoke our material system. Basically, get vertex attributes is going to go and fetch the current triangle data, current pixel data, using the barycentric coordinates, and prepare the shading data is going to go and fetch all the data we need from the textures and the current material. And then eval material, this is our physically based material system. This is where we're going to go. We're going to evaluate GGX. We're going to run the Disney diffuse BRDF. I'm going to give you a final result. Very fake roughness, a very fake way to do a reflection just because I didn't want to go into the hassle of running GGX here. And that's it. We're going to get that image. So the nice thing about that sample which we're going to release is that because it's Falcor and because Falcor support both ray tracing and rasterization, with 3 lines of code I can actually switch between the ray tracer and rasterizer-based renderer with shadows. It's the same sample, you hit spacebar and literally it's 3 lines of code. You need to create a different scene renderer for the rasterization instead of RT scene renderer, just called a regular scene renderer. And that's it. And this allows us to switch back and forth. You know, when we test our path tracing techniques and when we test ray tracing techniques, we can switch back and forth between ray tracing and rasterization. You want to show it now?
Let's run the demo.
Okay, we have a demo to show you now.
All right, so I'm gonna show a little demo we built. NVIDIA Research built on top of Near's, Falcor rendering library. So we built a kind of a lightweight render path solution, where different researchers, we're about 10 people working in the same code base, implement render passes in the same framework. Those render passes hooked together. Each one generates inputs and outputs. Here it's running on a single GPU. There are multiple GPUs in the machine, but we don't have multi-GPU support yet. This demo is shooting, first of all, it's shooting 1 ray for diffuse lighting at the hit point per pixel. Then it's shooting 1 reflection ray per pixel. And then at the hit points of the reflection rays, it's shooting 3 additional rays. So we're doing 5 rays per pixel. And then there's denoising filters applied. So it's running, I think it's running around 25, 30 frames per second in this case. It's fairly, a lot of things left to optimize, of course, but it shows that we can build something pretty complicated on top of Falcor by reusing a lot of the boilerplate code and abstractions. So this is, this lets us focus on the algorithmic development and not the thousands of lines of code to actually get something running with DX12 and DXR.
Thank you, Patrick. So, as promised, we're going to Falcor is already open source. We're going to release our DirectX ray tracing abstraction layer as part of Falcor 3.0 on April 10th. Other than that, Falcor supports DX12 and Vulkan on Windows 10 and Linux. We also have a bunch of raw API tutorials for DXR, and we're going to release some sample packs for ray trace shadows, AO, some denoisers, and a basic ray tracer. This is a list of stuff we currently have in our effects library. We're going to keep pushing the boundaries of what the visual quality inside of frameworks means. Like I said, 70% is a moving target. Game engines keep getting better, and we have to keep up. So we're going to keep adding things to Falcor. One last thing, we also have something called the Open Research Content Archive, because having good material system is worth nothing unless you can get good assets, and we were lucky enough to work with some partners who provided open source assets. So Amazon donated the Bistro. We got some good trees from SpeedTree. Nick, our own artist, created this Emerald Square, and Epic donated the Sun Temple. So you can go to developer.nvidia.com.org and get those assets, and please stop using Sponza, please. You can get Falcor from GitHub, and the last link for our developer blogs, you can get some more information about DXR and RTX. There's a good blog by Martin Stitch there, so I encourage you to go and read it. And I don't think we have time for questions, but we do.